Good morning, good afternoon, good evening, everyone, wherever you happen to be in the world. Welcome to Class 8 of DCT 302, Advanced Color Theory and ACES. You can hear from my voice that I'm still suffering a bit from the cold, or actually, as my doctor told me, borderline pneumonia last week. So thanks for your patience in deferring the previous class, and thanks for joining us today. Um, Last class 2 days ago was kind of an improv riff on the wide gamut topic and the gamma topic, responding to a couple of questions in the forums. And let me follow that discussion up briefly with some materials whose links that I will share with you. Sorry, I don't have them ready right now, but we will ship half a dozen odd links to you after this class, and you can consult these various basically reference materials, several on ACES, a few on color processing for cinema in general. So let's drop into that. So the first one is I guess you'd call it a white paper, but as far as I can figure out, Martin Bright, I guess he's a German guy, is interested in scene synthesis CGI, and he apparently just wrote this for himself. And he's talking about how gamma is dealt with in CGI. And I wanted to show you this white paper. And now I say white paper loosely because ordinarily you would expect a white paper to come from a company. He's clearly not a company. But I wanted to show it to you, and as I say, we'll share the links, because he's got this pretty interesting diagram showing what he considers to be a complete gamma correction pipeline through an entire CGI chain. And what he's basically showing you here is that in certain places in the chain, it's important to code perceptually uniformly. That is, to have a compact image storage scheme. And the example there would be, okay, so this portion of Martin's drawing, 8-bit texture, would represent sRGB values with gamma corrections. So what I would call R prime, G prime, B prime. And he's expecting that those values will come in from a physical light intensity, but be gamma corrected. I would kind of prefer that block to be drawn in the chain. But you get the advantage of storing in a compact fashion. So this would be a classic TIFF file. Now, of course, you can also store linear light data in a TIFF file, but it's very common, even with 16-bit TIFFs, to store with a gamma curve already. And then I'm not going to go over any of the details here, but Martin is basically showing you when you go out of gamma space into linear space, when you go back into gamma space in order to preview, and so on. So I offer that to you as just one of the resources available for you to take a look at on your own. And so, as I say, I'll ship you the link to that. Now, there's a couple of must-read items for ACES class digital cinema processing, and some of you may be familiar with these already. But the first one is using OpenEXR and CTL, written by Florian Kainz, but also obviously contributions from his coworkers back in 2007. And this document is a must-read. I think now that you're 8 classes into DCT 302, you'll probably find it a pretty easy read, but it's not immediately approachable until you've got some background in ACES philosophy and theory. The key point here is the diagrams that show transforms at various points in the pipeline. Now, you have to understand this document was written in 2007, just at the very beginnings of the ACES effort. So the acronyms have changed, basically. And you'll be able to figure out what the appropriate acronyms are, how these things translate into modern ACES terminology. So there you go. That's a must read. And then I'm also going to recommend 3 presentations which are available on the web, all of which are basically course notes, well, more or less, course notes for some talks. There was a special session, I think it's called a Birds of a Feather session, BOF, at SIGGRAPH. Whoops, this is not from that session. This is from SIGGRAPH session on gaming. So the title of this, it was a SIGGRAPH course, actually, 2010, on color enhancement and rendering in film, well, film and game production, but it was quite game-centric. And as you may know, the game developers are very much trying to achieve a cinematic look in their images. So there's a lot of shared technology between those 2 domains. And this is a pretty long presentation. It's 136 pages. So I'm not going to leaf through it or anything like that. But I just recommend it to you to take a look at. As I say, we'll ship you the link to this presentation. It's available online. Another presentation available from the same session at SIGGRAPH 2010 is from Joseph Goldstone, who's signing himself on this presentation as Lilliputian Pictures, because that's the name of his company from eons ago. In fact, that's the name of his company from such a long time ago that Joseph managed to get a 2-letter sorry, I'm having trouble with my drawing tools here. Joseph managed to get himself a 2-letter domain name, lp.com. He was a very, very, very early internet guy, and that domain is probably worth a small fortune now. Why he doesn't sell it off for a small fortune, I'm not sure. But Lilliputian Pictures is what he calls his little company, One Person, and that still exists. But he's now a full-timer at ARRI in Los Angeles, and very much a color science specialist and very involved in Alexa color. But take a look at this set of 35 slides from SIGGRAPH 2010. As I say, we'll ship you the link for that. And then the next one, a next resource for you, and some of you may have seen any or all of these already. The next one is, I guess you can call it a white paper. I think it was originally written by Jeremy Selan, S-E-L-A-N, a Sony Pictures ImageWorks guy in Culver City. Very good color science guy, coder. And he put this together. It's now badged as a white paper of the Visual Effects Society. And this is a very interesting, very good color, bridge between color science and color art. And let me leaf through this just quickly, because there's a couple of pictures that I want to show you from it. And oh, by the way, on the way through, I'm just going to have to take this up with Jeremy the next time I see him. but it's a characteristic of this diagram that Jeremy is showing us here. It's the classic XY diagram. But I have to tell you, I really don't like this presentation of the XY diagram. And the reason is that this diagram is presented here. And by the way, this is basically taken from Wikipedia. I mean, I wouldn't be at all surprised if Jeremy re-rendered it for his own purposes. But the reason I really don't like this is if you think about 709 space, 709 space lives pretty much in this region of the chart. Well, maybe a little tiny bit closer to the spectrum locus down there. And that's where the 709 colors are. They're only within that triangle. And they extend out to a saturated blue, a saturated red, and a saturated green. Really, really, really colorful. Way more colorful than this diagram is showing you in that region of green. And in fact, the chromaticity coordinates out here are like super highly saturated. In fact, this coordinate would be a laser. So what's being presented to you in the color is highly, highly desaturated compared to what it actually is. So I would just greatly prefer if this diagram were presented with colors within the triangle. And, you know, I'd even be happy with Rec 709, even though offset printing, you know, if you print this out on your inkjet printer, you're going to be able to achieve colors out to here. In fact, probably even out to here. But I think this diagram should be presented with these regions not shown, deliberately blocked out, with a note that says these colors can't be portrayed on your device. So as I say, I'm thinking I might just have to take that up with Jeremy as a complaint against his presentation of that color diagram. Well, there you see the triangle, but I don't like the colors. Oh, there's another issue that I have to take up with Jeremy. And, you know, this issue just came up for me again a week or so ago. It comes up periodically. You'll see all over the place, and even here you'll see from Jeremy. And Jeremy is a completely clued in, really smart, really good guy. But Jeremy is proposing here on the left-hand side of this page that with sRGB, the way you linearize it, you know, sRGB, as we know, is a gamma-corrected space. I put primes on the RGB. And, you know, we all know that it runs from 0, which is reference black, to 255, or if you like, 255, 255, 255, which is white. But in the middle, it's gamma corrected. So it's subject to a gamma curve on the way out from video signal code to linear light tristimulus. And I've been saying all along in this course that the power function is 2.2. But some of you might have seen this little piece of arithmetic before that has not a 2.2 but a 2.4 power function, and this conditional that gives a special treatment if the linear RGB values are less than about 4%. And basically this is inserting a linear segment to this curve down near black. Now, on the flip side, if you're building a camera, you absolutely need a linear segment near black. And then you follow that with the power function on the way up. And this is the curve that I'm arguing in 709. Well, 709 says you take tristimulus value to the 0.45, So in a sense, it's a power function with a gamma of 0.45. However, 709 says you take that power function, you multiply it by 1.099, and you subtract 0.099. And then 709 says you insert that linear segment. So what's really going on in 709 is that the power function extends down to about there, but you stitch in that linear segment instead. So instead of terminating at about minus 0.1, you terminate at 0. Now, this processing with the insertion of a linear segment is entirely reasonable in a camera. However, that is absolutely not what's done at a display, and you should not do that at a display. So let me think. This is Jeremy here is saying how to take device RGB, which is the sRGB numbers, and map them into linear RGB. But he's using a linear segment. Well, that's this curve. That's device RGB values into linear tristimulus. And my argument is you should absolutely not use a linear segment. Instead, the correct math is RGB raised to the 2.2. Now you may say, well, wait a minute, Charles, I've heard lots of people do this linear segment. Jeremy's doing it. Jeremy knows what he's doing. Surely you must really want to use the linear segment. Well, to give you my proof of that, give me a few moments on my other screen while I fetch up a document for you, which is the sRGB standard itself. So this document is IEC 61966-2-1, and this is absolutely the official sRGB standards document. Okay, so not only is this the official standards document, but take a look down here. Take a close look here. I actually bought it, so it is completely official. This is not a not a borrowed copy. Although I will admit I wouldn't be above borrowing things like this once in a while. So let's take a look at this document. So I should warn you, first of all, it's a mixture of French on the left and English on the right. It's in two languages, so you only need to look at the right-hand side of these pages. So we go through, there's an introduction, scope, normative references, blah, blah, definitions, blah, blah, reference conditions. Okay, now let's look carefully at this reference conditions business. Here's reference conditions in English. So what does sRGB say? Well, sRGB says thou shalt have what they call a display luminance level, which really we could call peak or reference luminance or reference white, if you like, of 80 nits. You can call that a nit if you want. Now, I have to tell you that this is not realistic, unfortunately. The typical number here on any sort of modern display that you just go out and buy, either a computer display or a consumer television receiver, will be around 4 times that. And if you're doing VFX CGI work, you'll want to cut that peak luminance so down, but you might not want to go as low as 80. And, you know, I've made mention previously several times that for HD, it's a sad story today that there's no standard, but the standard should be around 100 nits. So if you're in VFX CGI, you'll probably be wanting to run around 100 nits. Anyway, continuing on sRGB, they say white shall be D65. Fine. Display offset, and here they say model offset, and they're really referring to an equation that describes what the idealized or the model of the display reproduction is. And then they say that display input-output characteristic, and input is bogus. There's no input, there's just output. And they say 2.2. Well, that's the gamma. And then they say the chromaticities are those of Rec. 709. So it's really, really nice that sRGB has precisely the same chromaticities, little x, little y, as 709. Now you're thinking, oh, little z, it's off the scale, off the page. Well, doesn't matter, because little z or little z is just 1 minus little x minus little y. So we don't need it. Actually, it is, of course, off the scale, and it is available on the next part of the page. There it is. Now, here is the key part. The sRGB standard says the reference display characterization is based upon CIE 122 blah, blah, blah. The reference display, here's the important part. The reference display is characterized by the equation below. Here's the equation. It's got 2.2. That's the end of the story. Now, there's a whole other thing later in the document, but that's not describing the idealized display mapping. This is the display mapping. This is from nonlinear RGB, and you can see they put the primes on it, which is good. And then instead of VS, I mean, this is really not good notation. They really should call it T for tristimulus. But it's just 2.2 gamma. Whoops, that's not a gamma. 2.2 gamma, end of story. So as I say, I'm going to have to take Jeremy up on that because I disagree with his interpretation. Now, we're headed here in, I'll go back to Jeremy's document because I was just paging through it. I'm paging through it to find these drawings. Now, we'll send you the link, download this, read it. But on the left-hand side here, Jeremy is showing you what he calls bokeh, which is the classic photographer's term for the way a lens affects out-of-focus elements. So here's the word bokeh. And as far as I know, it's a translation of a Japanese word. And I'd love to know if any of you know what that's about. So what Jeremy is saying basically, if you do scene linear processing, in particular filtering, your filter results look something like this in linear space. But if you filter in nonlinear space like sRGB, your results look like that. And Jeremy's saying here basically, and I agree with him 100%, the specular highlights filter looking way more like cinema if you do the processing in linear. So basically up here is linear, light, or let's say scene linear, which would be technically correct. And here it's nonlinear, or if you wish, gamma corrected, but I really don't like that term. So here's Jeremy's description of why you really, really want to have scene linear in the midstream, the main portion of your imaging pipeline. And this is why we do it. This is what ACES is all about. Okay, so let's see what else I've got. I guess I've got two more things for you. I highly recommend this document, which you can see originates in Japanese, but it's actually an English document. And this document is, um, you can see from the bottom of this page, it's an article in the Fujifilm Research and Development Journal. So this article is from our colleagues, and these guys have been participating quite heavily in ACES. And they're basically describing it to all of the Fuji customers who read the Fuji R&D journal, which is published in English. This is a lovely, lovely introduction to ACES. So I highly recommend you read it. And we'll send you the link. Now, there's a SMPTE journal article quite recently. This is, well, a year ago, April 2012. And, you know, the ACES is not final even today, let alone a year ago. But this is about displaying ACES content, well, on a Dolby monitor, because these guys are all from Dolby. And I'd recommend you read this one if you can get a hold of it. I don't think that we're able at FX PhD to distribute this to you, but it is available linked from a SMPTE webpage. I'm sorry, a Dolby webpage. Dolby has basically put this up for grabs. And, you know, you could find it with Google just by typing in the title, but we'll send you the link to this article, but we can't send you the article itself at the Dolby site. And this article shows you a bunch of graphs about the mapping from ACES to OCES. And I think yesterday I made mention of the of the RDT, which is the specialized, special distinguished case of an ODT. The RRT goes to P3. And I think I made reference to the fact that ACES 1.0 in ACES, well, in OCES space, I'm sorry, so OCES 1.0 after the RRT, you would like to map through the RDT not quite to peak projector white. And this article confirms that interpretation, and I haven't had time to go and look through the official Academy documentation of the current state of the standard, but it's not very much different than it was a year ago. And this article explains somewhere that OCES 10.0 maps to P3 projector maximum. So in OCES space, you've got about 2.5 stops, I'm sorry, 3 1/3 stops up to projector maximum, but you would expect the RDT to roll that off. And the extent to which it rolls it off, I'm not quite sure, but my assertion to you several classes ago was that it's common practice in cinema to place diffuse white, like white shirt white, white piece of paper white, color checker patch 19 white, to place diffuse white around 1 stop below projector maximum. So I'm guessing that the RDT will probably want to map OCES 0.5 to about P3 linear light 0.5. And the P3 domain then for display or distribution purposes will be subject to Digital Cinema Gamma 2.6. But if you want to know the details of those mappings, I mean, you can always download the Academy code. It's on, I believe, GitHub. So it's open now, even though it's not quite 1.0. But as you could guess, it's quite time-consuming to dig through all of that. So the Dolby paper is quite useful. Okay, and that's, I think. Oh, there's one other link we'll send you. We'll send you link to this paper, which is available on the web, which it's from a guy who's, you can see, is listing himself as École Nationale Supérieure, which is one of the high French universities. But he's working with Micros in Paris, and they've been working on ACES input device characterization. So they're basically building ACES IDTs. And so here's a 5-pager telling you roughly what they're up to. So, you can see even just from a cursory look that they're wanting to get access to spectral sensitivities. This one is from a Red 1 Mysterium X. And they also need to know the tone response curve, or the coding curve of the camera. They're using a pretty special illuminator, so this is really laboratory grade. Whether you have to do that, I'm not really sure, but they're doing that. And they've got monochromator. It's very high-end piece of laboratory instrumentation. So it isn't really easy, but the rest of the class I'd like to tell you roughly how you build an IDT. And I'll ship you the link to this this journal paper. You can read that for your homework assignment. Okay, so now with that stuff covered, okay, so we're going to talk about color transforms, and I'm using Steve Hilbert's Nerd Girl as our icon or visual reference for this part of the talk, but I'm going to have to start sketching these things myself instead of using other people's art. We already know about a bunch of standard primaries, and we've talked about these already in different classes. Obviously, the one we like for HD is Rec 709. I say here that it's supposedly the international standard for HD. I no longer use TV, but I have to warn you that large amounts of HD were mastered on CRTs. In fact, during the period about 1990, when 709 was agreed upon, and let's say 2010, so for 20 years after the adoption of 709, the only display devices available were CRTs, certainly in the studio. And Sony and all of the other CRT manufacturers never made a CRT with 709 phosphors. So you have to just be aware that all of the material mastered in HD during those 20 years was mastered with either EBU or SMPTE primaries. And only with the emergence of 709 flat panel displays have we finally come around to mastering HD material in 709 space itself. Now, as you saw a moment ago, and I showed you the standards document itself, sRGB uses the exact same primaries. So this is a very good piece of news. However, none of those primaries are wide enough for cinema. So we have to talk about another set of primaries, and we can start here by mentioning Adobe RGB, which is really for graphic arts, of course, not for cinema. DCI P3 RGB, this is our cinema space. So this is the big one for us. And it's distributed in XYZ, but that's just a transform back and forth, and no gamut mapping takes place in that transform today. So, in some sense, you can consider those to be interchangeable. Now, where we're headed is laser primaries. And we know that IMAX has already licensed some Kodak patents for laser projection in digital cinema, and both Barco and Christie have demonstrated laser projectors. So, we're not sure where that goes, because today we want to master it in standard P3, and we really don't want to have a wider color space. We're not sure how you would master for lasers and then shrink to P3. There's big gamut mapping challenges here. But let's, for now, just talk about the DCI P3 case. So you know that we can describe primaries by the little x, little y coordinates. You've seen these before. We know we can transform back and forth among those coordinates, and that's just a linear light 3x3 matrix. The colors remain exact, but the numbers change. So different RGB systems have got different RGB numbers for the same color. And this approach obviously doesn't do any gamut mapping. If a color at one end of the transform goes out of range, typically out of the range 0 to 1, these transforms clip. And you know, it's good news with ACEs that you can have numbers smaller than 0 and greater than 1. So you don't have to clip in ACEs space, but when you go out to a monitor or a projector, you know, clipping may be involved. And the gamut mapping required to kind of carefully go from one color space to another color space, like from P3 cinema space to 709 space if you're mastering Blu-ray, that's gamut mapping, and that's complicated. That's more complicated than just a 3x3. And there's math, and my orange book explains all this math of how you convert among different RGB spaces using a 3x3. Now, I don't think I've given you this story, but again, I'm not quite recovered from being kind of dopey and stupid from being ill. So stop me if you've heard this one before, or you might even want to hear it again if you have heard it before. There is an idealized way to capture scene information. And this idealized way would tell you exactly what filters to use in front of a camera. And these filters, are called X bar, Y bar, and Z bar, or Z bar, depending where you're from. And these terms refer to the curves. When you integrate, you know, if you start with some spectral stimulus in the scene, like a tomato, and you integrate it under the Z-bar curve, you get big Z. When you integrate it under the Y-bar curve, you get big Y. That is exactly luminance. And when you integrate it under X-bar, you get big X. And this is very, 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 very similar to blue. Z-bar isn't really that close to red, but you know, it's something like red. This, I should say, is a mistake. This should have said Z. So that's the perfect way to capture a scene. And so your next question might be, okay, if I've got those big X, big Y, big Z numbers, how do I build a display that just directly displays them? And the answer is, well, there's an infinity of different display curves you could use. But if you just take one example of a display that produces power at 470 nanometers, 550 nanometers, and 600 nanometers, then you would generate this much power from the big Z channel, this much power from big Y, this much from big X. Now, big X is pretty simple. That could just be laser power at that particular wavelength. But the other two, you cannot generate directly because they've got negative amounts of power. This approach doesn't work. So let's take a different tack. Let's say, well, okay, if that doesn't work, what if we start with colors at the display that we know we can make? And these curves are the three curves of a Sony Trinitron display. And let's do the calculation backward from there to ask, what are the correct spectral sensitivities? And if you do the math in the backward direction, you find these are the spectral sensitivities. Now, these sensitivities have got a special name. These are called the color matching functions for 709 because I used 709 primaries in the display. And you can see that where on the previous case the X bar, Y bar, Z bar curves were all positive, these ones now have got negative going lobes. So you cannot build these curves directly, or at least you can't easily build these into the camera. Now what you could do is you could build a camera that had this curve, which is all positive, and this curve, which is all positive, and then in the signal processing, take this signal and this signal, but subtract this one electronically. Now, this electronic circuit would give you exactly the equivalent of building this filter, even though it has a negative lobe. So the key idea here is we can use signal processing or arithmetic in the numbers. You know, these are the numbers coming from the sensor. We can do arithmetic here to compensate, in some sense, the shape of those filters. Now, an engineer would look at this set of three graphs and say, well, yeah, that's a pretty big excursion there. So we're not likely to get really great color without doing something here. But, you know, we're engineers, so let's just ignore those negative parts of the curve because they're not very big. So we could get away with a 4-channel camera. However, there's a way to do it with 3. But I wanted to introduce this idea to you of doing signal processing on the numbers to get the colors to work correctly. So you start in the camera with curves that look something like this. Now, this set of curves, I can reveal to you in secret, is from an old Sony CCD camera. It's from an HDC F500, really old one, like almost 15 years old. And that camera used a beam splitter assembly. And I showed you that whole beam splitter business of splitting out the red, the green, and the blue into 3 separate sensors. And there you can carefully manufacture the curves by making suitable filters. Now, of course, we all know that modern cameras use Bayer sensors or some kind of mosaic sensors, typically RGB. And in a modern camera, you've got less control over the shape of that curve. And typically on a modern camera, the curves will kind of look more like this. They don't have such fast transition bands as the old CCD cameras used to have. But nonetheless, in a camera, even an old one, and certainly a new one, we start with curves like this. And we take those curves and we basically add and subtract each channel from the other judiciously, a little bit like I showed you a moment ago, to produce the signals that we call RG and B. Now, whether the camera delivers signals, I mean, we can call it camera red, camera green, and camera blue. You could call these device primaries or optical primaries, but they're typically pretty far from what you need to produce proper color. And if you try to just put the R, the G, and the B directly into a display without a matrix, you get very poor results. Now, I'm going to show you that in a moment. But the better idea is use a matrix which basically has the effect of taking these camera curves and synthesizing them into this set of camera curves. So we electronically take some minus green, that's this portion, and mix it into the red channel. So this is the equivalent matrix sensitivity of the red channel, but it's got a bunch of minus green, and it's typically got a little bit of plus blue as well. To produce green, the matrix subtracts a little red and subtracts a little blue, typically. So, basically we've got a matrix which is taking RGB from the device, and it's making a dot product to produce RGB in the 709 flavor or in the ACES flavor. So, we'll in modern cinema cameras, we want to be producing ACES RGB, and in fact, this matrix would be part of the IDT. So now let me give you a little flavor of how you figure out what the matrix should be. You start with practical camera sensitivities like these. And these are sensitivities of a Mosaic camera whose identity I will not reveal to you. But I should warn you that this isn't actually a good idea to use these sensitivities directly. Look at all this energy that's happening above 700 nanometers. Nobody can see that energy. This is the IR domain. And it may be tempting for the camera designer to cheat, to get more sensitivity in the red channel by just leaking some IR in. But as you can imagine, this would turn out to be a really, really bad move in practice. And so what we would do instead is we'll put an IR cut filter in the camera. And this is typically a separate layer, often placed on a piece of glass immediately in front of the CCD or the CMOS sensor. So we cut the IR to avoid having IR intrusion into the picture. And in the following calculations, I've excluded the IR component. So then the next step is take a color checker. And my friend David Corley, DSC Labs here in Toronto, makes really high-end, really lovely charts for lining up HD cameras. But honestly, he doesn't have one which is perfectly suitable for this task, even though they're way more stable and way better than Macbeth. So let's just think Macbeth. And if you remember the white paper from the German guy, Bleit, showed you a Macbeth chart, and I think you know what that looks like anyway. So you start with a Macbeth color checker, you make some measurements, and you plot where all of those patches end up on your Macbeth chart. On the CIE little x little y chromaticity diagram. Now, here, I mean, you think, well, there should be 24 dots. And you think, let's see, I'm only counting 19 instead of 24. Well, that's because 6 of them are piled up on top of each other. Those are all of the grays and the white. They're all piling up right on top of the white point, which is typically in the middle of the chart. And the color checker, you can see, has got a few chips which are right on the verge of being outside of gamut. This is the red, which is not very close to the spectral locus. This is the orange. This is the yellow. They're right on the gamut limit. And this is the gamut limit of 709. So these are instrument measurements where those colors are supposed to hit. So now, second step, let's take the camera, point it at the Macbeth chart, and then just directly take the RGBs, hook them up to a 709 display, and see what colors we get. These are the colors you get. So basically, if you don't do any electronic processing in a matrix, you find the colors look really undersaturated. They look like pastels, and the picture looks wrong. Now, the picture's not being decoded correctly because your display is in 709 space, and your camera, well, We don't yet know exactly what space the camera is in, but it's certainly not in 709 space, it's in camera device space. So we're not looking at it correctly. We need to make some modification to the image data. That's what the 3x3 matrix is going to do. So that's the result of uncorrected processing. So what do? Well, we do an optimization procedure, and you can think of it loosely like the least squares issue, to solve for those 9 numbers in the 3x3 matrix. And the dominant effect of that is going to be bringing the saturation out to what it should be. So in essence, what we want to do is we want to find the 3x3 matrix that pulls these colors out to where they're supposed to be. And you'll find that that matrix is going to have fairly large terms on the diagonal, and it's going to have some negative terms off the diagonal. For example, I explained to you that the red channel will probably want to be produced with a fair bit of negative green. So we're going to come into this matrix with RGB, and the red coefficient is going to be some fairly large number. In fact, it might be as big as maybe 1.4. But we want some minus green, maybe minus 0.4. And this will be built into the matrix. Now, historically, that matrix would have been right in the camera head. So in a typical HD camera, that camera delivers RGB that's suitable to be connected directly to a display. So that matrix is in the camera. It's accessible to the camera menus, and the videographers and cinematographers sometimes know how to mess with that. But you can turn it off. And in the early days of the Panavision Genesis, the recommendation from Panavision was turn it off. Don't do any processing to the image data. Just record the image data so that when you bring it into post and DI, you haven't baked in anything. It's just sensor data. But if you turn it off, of course, if you then look at it directly without any correction, looks like it's undersaturated. So we're going to be building this matrix. We do it with an optimization procedure to compute those numbers. And when you correct the device data, you map the colors out to somewhere reasonably close to where they're supposed to be. So that's the result of correction. This is the measured color science values, if you like, the calibration values, and they're not the same. I mean, even after correction, they're not the same. So there are some errors, but we hope those errors are reasonably small. So that procedure that I've just explained to you is the procedure that goes into making an IDT for ACES, or in fact making a matrix for any camera for any sort of color space. But the particular thrust of DCT302 is making ACES work. Now, you're hoping that either your camera vendor or your grading system vendor is going to be providing you with IDTs. And, you know, I guess generally it would fall to the camera vendor to make the IDTs, but they may make them well, they may make them not so well. And, you know, I think there may be tools that become available to make IDTs. It's still an emerging area. So I don't have any answers for you on that front, but I wanted to give you a good, firm notion of what's going on in how those IDTs are made. And if you want to know more about that, you can read the article by Serlet, the one that I'll send you a link to. That, I think, oh, and sometimes you end up with matrices looking like this. So for the particular camera example that I showed you at the front of this section of slides, this is the matrix that I computed, which is the part of the IDT. The other part of the IDT is just the compensation for the log curve or the gamma correction. And that's easy. That's just math. Okay, so, and I've got one little tiny piece left. Then, all of the modern cameras today are using mosaic cameras. They're single sensor cameras. They've got mosaic filters, which are literally fabricated right on top of the silicon die that has the photodetectors. They're obviously laid down in a 2x2 pattern, and you know that whole story already. But I want to mention in passing the Foveon chip, which you might have heard of, has got a process of separating colors through the absorption depth of the photons in the silicon. So basically, photons get converted to electrons in the top micrometer or so of the silicon. And the Foveon guys made this very sophisticated chip that pulled them out into 3 separate signals, and they didn't have to do mosaicing. They didn't have to do demosaicing. And you think to yourself, that's a great idea. That will probably work spectacularly, but actually it doesn't. So now that you know what I've told you about 3x3 matrices, let me tell you why it doesn't work. It doesn't work because the elements in the matrix get way too big. The spectral sensitivities, because they're just a function of the absorption depth in the silicon, look like this. And these are not nice sensitivities at all. I mean, you can just take one look at this and say to yourself, well, gee, in order to get a reasonable green response, something like that, I'm going to have to take a whole lot of blue and subtract it from the device green, and I'm going to take a whole lot of device red and subtract it from the device green just in order to synthesize this curve that I want for green. And when you do all the math, you do the arithmetic, you find out that the matrix is like this. Now, if you look at this matrix, you see, okay, this matrix involves taking device red, green, blue, like so, and it involves taking red, multiplying by 2.6, green by minus 1.4. These are pretty big numbers compared to, say, 1. Look at this number. You've got to take minus 2.5 red out of the green and minus 2.25 blue out of the green. And to compensate and bring the gain back up, you've got to multiply green by 5.7. These are unbelievably huge numbers. And what happens here is basically 1 millivolt of noise, like a little tiny, tiny, tiny bit of noise on the scale 0 to 1, gets multiplied by 5.7 in the result. In fact, it's worse than that, because then a millivolt of red noise and a millivolt of blue noise, they also get multiplied. So, and they just get added up. So the noise in the blue channel ends up being something like 10 millivolts. So basically, the matrix, which you absolutely have to do to get the colors correct, is multiplying the noise by 10. So you think, that's going to suck. That's going to be really terrible. And in practice, the Foveon cameras produced really noisy images. In fact, the images were so noisy that in order to get performance back comparable to everybody else's mosaic cameras, you might as well have been shooting mosaic to begin with. So what I hope you gather from this little section at the end of today's class is that the matrix really matters in terms of the performance of your imaging system. And these matrices are in every IDT. So if you're in VFX, you're in grading, you're doing image acquisition, it's a good idea to understand something about how they work. So there you go. There's your overview of matrixing and IDTs and color mapping and 3x3s. And that's the top of the hour. And it's 03, so I've been ranting on and on for about an hour. We'll have another class next week, which, if I'm counting correctly, is class number 9. And we do have to do a little bit of YCBCR Lumichroma space, so we'll do that next week. But if you want, it's 03 and I want to end within the next 5 minutes. But if any of you have got any quick questions, okay. So I think if you don't have any questions, visit the forums. And, again, apologies for my illness. I've been somewhat absent from the forums. But I'll go and check that. You can ask some questions or have some discussion over there if you like. John is giving me the thumbs up to go a little bit over. So let me just do a little 5-minute section on something else. So let me get it up for you. This is a 20-pager that I've asked Ryan to distribute to you as materials for today. Now this, you can see from the rubber stamp, is draft, confidential, unpublished. But I want to float this out to you. It's a note about something which sounds like it should be really unbelievably simple: contrast and brightness. It's those two knobs, those two pesky knobs that are on the face of almost every display and monitor that we use. And it's not simple. It's actually very complex. And the short story is I started working on this about 2 years ago, kind of challenged by my colleague Mark Shubin, who's a very, very good senior accomplished HD guy. And he and I had a long conversation about brightness and contrast. And that really is the genesis behind this note. So let me just go over it really quickly for you. I mean, these are on billions of pieces of equipment, and the words brightness and contrast do not represent, well, I'm sorry, let me back up. The words brightness and contrast in common language are not the same as the words contrast and brightness used as the labels of these knobs. And I'm putting the labels of the knobs in capitals and explaining the differences. And I'm making a little joke here, calling the pot black. The black I put in capitals because I'd like to call the brightness control black level instead of calling it brightness. So let me give you the quick story. The quick story is that contrast and brightness come from the old days of CRTs. And in CRTs, contrast happened first in the signal chain, and brightness happened last. In fact, brightness was typically connected directly to the CRT. So, if you think of order of operations, basically we've got a multiplication by contrast followed by an addition of brightness. And then, as all of you guys have heard many times in the course, there's gamma. And this is going to be something like 2.2 or 2.4. So really gamma then you can think of as an operation that happens after brightness and contrast. So here's the old analog circuit that you'd find in an analog TV set. And now I show you this little schematic to suggest to you that there's not only kind of an overall global brightness and contrast, but there's also something called drive and something called bias And again, this is a multiplier. This is an adder. And again, the multiplication comes first and then the addition. But these controls are individually R, G, and B. So the drive is also called gain. And this is the position where white balance or color temperature is adjusted for a display. And then the bias adjustment, also called screen, also called in home theater circles RGB low, this one being RGB high. Because really, you know, the gain affects the white and the offset affects the black primarily. Now, in modern displays, there is, like in an LCD or a PDP or a DLP, there is no physical phenomenon that causes the black level to shift channel to channel. These should be abolished. There's absolutely no need for them in the modern world. The trouble is that none of the display vendors has got the intestinal fortitude to eliminate the control. And also because the display manufacturers get confused, they think that the users use these controls to adjust particular pictures, which they don't. So anyway, just so you know what the gain and bias controls are, the separate RGB gains and biases. Now, I'm showing you this photograph from the old days of IBM, where they first introduced these icons, and this is in about 1984. They didn't have any names for the controls. You know, IBM was producing products internationally. They didn't put words on the front panel. But if, you know, I've gone and looked at the service manual for this original IBM monitor, and on the circuit board, this one is called out as contrast, and this one is called out as brightness. And that's generally how those icons are assigned in the modern world. And roughly speaking, the way that you adjust them is you adjust this knob, which really should be called black level, adjust this one for the blacks, and then tape it off, don't use it. You know, the circuitry today is quite stable. It's no longer necessary to adjust this to compensate drift, because basically there is no drift anymore today. And the one to use to achieve the white level that you want is this one. And, you know, I'm suggesting that 100 nits would be good if you've got an instrument, but that's really the white level control, and I kind of wish it were called that. Now, I go through a long discussion in the paper about how the gain control, or it's called contrast, basically scales the curve. So you got this, 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 but all relative to the 0 point. So this is the multiplication operation. And then after that, you shift. So the lower curve goes here, and then here, and then finally here. It's just shifting with the center point typically centered on 0. So what's happening is you're scaling and offsetting the x-axis, the pixel value, and you're moving the curve. So now it's unfortunate that the monitor vendors don't give you these gain and offset numbers. Here, this is the amount of gain, and this is the amount of offset, or a bias. And the equation, like, this is unbelievably simple. It's just y equals mx plus b, where x is the signal coming in from 0 to 1, m is the gain, b is the bias. And typically, the bias goes plus minus zero point 0.2, and the gain goes typically somewhere from 0.5 to 2. But these numbers you don't find on the face of the display. Instead, you've got a slider that goes um, like in this example, here you've got contrast running. Well, at the moment the contrast is 60, but it looks to me like the contrast is scaled 0 to 100. So they don't tell you what the gain number is. And you know, it's very, very unusual that you should have that brightness value depart from 0. Because in modern day displays, the circuits are very stable and the reflectance off the faceplate is very low. So typically you want the bias to be very close to 0. So with that, I think I'll wrap up that discussion. You've got another 15 or so pages to go here that you can read about how all that works. If you've got any follow-up on that article, I'd be happy to talk about it. But that's the short story of brightness and contrast. And you know, you should go and do the brightness and contrast thing before you calibrate your display. And then your display calibration will tell you whether you've done it correctly or not. So there you go. There's class 8 of DCT 302. And we'll be looking for all of you in a week's time for class 9. Thanks very much for joining us.